BMS doing for R&D and what our field is starting to focus on for this new field of sub-GeV dark matter. So I'm going to cover a couple things, starting sort of with, if we're looking for low mass dark matter, what are the design drivers there, what are the current challenges, and then where do we go from where we are. So what are the efforts that we should start putting time into, and these are all things that are starting to come up in some of these quantum information science, and do have basic research needs proposals. So I've pulled out a couple of the interesting examples, but using them as straw men for sort of where we go, how we do the R&D, and what the challenges we're going to face are. So this is a picture of the classical, or sort of, this is the parameter space we've been looking at dark matter in for the last few decades. The y-axis is the proton spin-independent cross-section, the x-axis is mass. And so you notice a lot of the recent efforts, we've been pushing very far down at high mass. They all do this sort of scoop-up behavior at low mass. And this is a real distinction that we can make because of the kinematics involved here. So at a mass of about 10 GeV, you're going from having a dark matter that's much heavier than all of our detector media to something that's much lighter, and you've become very threshold driven. So all of the experiments that are down here have done various things to lower their thresholds, and if you have some readout technology that can do about a keV threshold, you can do any sort of dark matter search up here, and it's more of a background issue and exposure issue. So if I take a look at in the mass versus maximum recoil energy, so if I take a dark matter particle moving at the escape velocity of the galaxy with a given mass in different media, this tells me my maximum recoil energy transfer for that given mass and given target. And there's two things that go on here, right? So at high mass, the best thing I could use that gets the most energy transfer is xenon. The worst thing would be helium, right? So higher mass is better. And then we also have different types of recoil. So I have nuclear recoil or electron recoil. This is actually a coherent recoil, not an elastic recoil that would be limited. The elastic recoil is limited to about 4 GeV. But the nuclear recoil is also better. As I cross that 10 GeV line, they flip. So electron recoil becomes kinematically favored. It doesn't fall off quite as fast with mass. And the scattering does not care about the target for electron recoil. And for nuclear recoil, now the lightest thing gives you the most efficient energy transfer. So when we talk about light dark matter, we're basically talking about electron scattering experiments or nuclear scattering experiments in light nuclei. Right? And so another thing that we've started to use, so when we're moving into lighter mass, we don't have this nice wind miracle where something at 30 GeV roughly has the weak scale interactions, and that's a nice thing to target. Since we're moving to a different mass range, we still need something to target. So what's been done now in the literature is we look at two different methods for producing dark matter. The early universe as a target to aim for our experiments. From this thermal annihilation target, basically to reproduce our relic number density, we can relate the coupling strength to the mass, either for a secluded freeze-out where some dark mediator is producing a relic abundance, or a direct freeze-out where you produce the dark matter in the early universe, and a lot of these will be like dark sectors theories, but this is anything with, basically to produce this dark matter, anything with some sort of mediator between the dark matter and the standard model. Right? And so you have some freedom here if you choose some characteristic values of the coupling strength. In this case, it's just the dark coupling strength. In this case, it's both vertices. You can get a line basically in mass versus coupling. So this is the sort of plot that's been shown a lot in the literature now. So now we're looking at the electron recoil cross-section, and now the mass scale is not GeV but MeV. And we're going from about a few TeV all the way down to a keV in mass. So this is for the freeze-in paradigm. And for freeze-in, you have a momentum-dependent cross-section, so you get a lot more scatter in these lines. These are all the same amount of exposure, but just depending on the particulars of your setup. So this is the case where you have sort of a standard light dark matter scenario where you have all your events pushed up against your threshold. So you're entirely a threshold-driven experiment. So what's been going on is anyone proposing new technology, you have to make some sort of case, well, I can reach the freeze-in line with a modest amount of exposure. And so this is really the target to hit. And this was the state of the art a few years ago. In the last 18 months or so, there have been 3 new papers, one from CDMS, 2 from Sensei, which is a CCD-based experiment that has started to carve out more space. But this is a growth area, and you can see where the current nuclear recoil constraints are. So this is the paradigm we're working in now. We're thinking about how to get to these freeze-in or freeze-out lines as they may be, and how to do it with either existing technologies we can push a little harder or with new technologies. So this is the, when we talk about the whole space now, not just focusing on WIMPs, but when we really back up and say, what are all of the different things that could be dark matter without injecting our theoretical or experimental biases in here? So this is from the Cosmic Visions report, but we can get anything from, QCD axion or ultralight dark matter, which could be axion-like particles, all the way down to the Planck scale, and then also things like hidden sectors dark matter, thermal relics, asymmetric freeze-in dark matter, Simpson elders. So all of these models, these are all, they've been covered in papers over the last 5 or 6 years pretty thoroughly. What the signatures might look like, how you detect them. And you can see they extend above WIMPs, but also down here. So, there's plenty of theoretical explanations for dark matter in this mass range. And, at about a keV, you have cosmological constraints on fermionic dark matter. So below here, these candidates have to be slightly different. But again, all the stuff down here, this is electron recoil preferred. This is nuclear recoil preferred. So if we really want to get down to EV sort of scale masses, these are going to be the ER searches. And we can still get down to about an MeV, as I'll explain a little bit, with nuclear recoil, but it's not quite as clear a picture as it was. So CDMS and a few of the other experiments, we use semiconductors to do this electron recoil measurement. And the reason is because these semiconductors, and in particular silicon and germanium, have an indirect band gap. So what that means is if I have some sort of energetic deposit in the crystal, I can produce electron hole pairs, and there's actually both an energy and momentum transfer, a net transfer at the end of the day, where I generate an electron hole pair across my band gap, it emits a phonon down into this band, and then for it to recombine, it has to emit another phonon. And so for a really high purity crystal, this creates an incredibly long carrier lifetime. You can generate an electron hole pair, drift it a long way off to a really sensitive measuring apparatus before it recombines. The direct gap, that's not so simple. That being said, there are people starting to look into using things like gallium arsenide. Tin is also technically a semiconductor. It's also a superconductor, so there's been some proposals. Some people might call this a Dirac material, but it's really low band gap stuff. But basically, this is a way to turn the signal into something athermal, so you can read it out above the quantum noise limit. A really interesting thing that has come out of all the research into organic and inorganic LEDs is that these are all semiconducting materials. A lot of them have been discovered for their emission properties in various visible ranges, but there's been a lot of expansion from silicon and germanium and gallium arsenide, which are sort of traditional semiconductors, into all of these weird things. One thing I'm going to point out is diamond is also a semiconductor, so I'm going to talk a little bit about using diamond as a detector later in the talk. But a lot of these are now also being explored because of their polar properties, so that's at the end of the talk. Basically, there's a benefit to having a monatomic lattice, but there's also interesting physics that you can do when you have a diatomic lattice. So this is cool. We can ask our material science colleagues to help us out with this kind of stuff. And then finally, if we're talking about the ultimate in still quantized excitations in a material, we can use superconductors. So a superconductor is basically just something with a band gap that is correlated to its critical temperature. The lower the critical temperature, the lower the band gap, and we're talking for these classical superconductors, band gap energies on the milli-eV scale. So the particles you produce are not electrons and holes, they're quasi-particles. They have this weird dispersion relation that's not quite what you'd expect it to be, but they still act as something in which you can create quantized excitations that are reasonably long-lived, collect them, and infer what the deposited energy was. So some of the ones that are used commonly are niobium and lead, People have been talking about using tantalum as well as aluminum as targets for dark matter. We'll cover that a little bit at the end. But these are sort of the range of different materials that have this band-like structure that you can use to separate athermal excitations from electrical backgrounds. So the picture for dark matter, before I go into any details, this is sort of what the community has put together recently, and I guess this is almost 2 years old now. Is if you use different technologies, you can get down to different mass scales depending on what you're looking at. So on the bottom here, this is electron recoils. Primarily gets you down to a few hundred keV. You get to go to superconductors, get down to the sort of the fermionic limit here. In terms of nuclear recoil, at the time there were only a couple proposals. There have been a lot more now. Superfluid helium, this is a cool system with quantized phonon states. Not going to talk about it today, but it's very interesting stuff going on. This is one of the biggest areas of research into nuclear recoils or sub-GeV dark matter. So if I map all of these different materials onto the plot I showed earlier, this just shows you why you need superconductors and liquid helium to get down to these really low masses. They have band gaps on the order of milli eV. You need milli eV to do much better than an MeV in nuclear recoil and about a keV. So these are our options for where to go. Of course, we could get lucky in the dark matter, could be moving a lot faster than we think it is, and then there's some less stringent. We could also get unlucky that's moving slower, and the problem is harder. But this is the basic path forward.
So there's difference in detection technique for each of these.
Yeah. Yeah.
One is for particle.
Yeah.
So for helium, is scintillation effectively for?
No, so helium is still a nuclear recoil. So we're still talking about a little bit more than an MeV at the minimum. Yes, these were tops. So it's a little bit misleading, but to get it all into one plot. So I don't want to go too much into the math of this, but what's helped the field significantly in recent years is there have been a few papers that really lay out the kinematics of electron scattering in semiconductors, which is complicated by this thing that I just called I, which is this overlap integral that incorporates the phase space in the crystal with the scattering kinematics. What really matters here is that you have density in the mass of the target. So this is basically the nuclear density of the target gives you a higher rate. And this is scattering. And then there's also absorption. And in absorption, what really matters is this term, which is essentially the complex conductivity of the material. So something with a high complex conductivity, as long as it's not self-shielding, is a really sensitive probe of bosonic dark matter. Something that is very dense in terms of electron density is very good for electron scattering. And so these are, Ruben Essig has sort of led the field on this sort of prediction for solid state as well as for xenon. If I look at different dark matter masses as a function of the number of electrons produced in any of these materials, I basically see that my maximum sensitivity comes at the 1 and 2 electron bins, right? And this is logarithmic, so if I have a threshold of 4 electrons, I need a much larger exposure than I would if I had a threshold of 1 electron. So the challenge here is making detectors that have single electron resolution and sub-electron thresholds. The other difference here is that xenon, compared to silicon and germanium, the ionization energy is much higher. And so at some point, this bottoms out much quicker than these. So if you have a perfect detector made of silicon, germanium, or xenon, the germanium is going to get you the lowest of the three because it has the smallest energy to create a single charge bond. And then for this bosonic absorption, things get a little bit interesting, right? So the idea here is you have some bosonic dark matter that mixes with a photon. So at the end of the day, what you're using is photoabsorption data, and you're assuming some coupling between the dark matter and the photon, and once you have a photon, you know how it gets absorbed. So for something like silicon, there's a resonance in energy and therefore mass of the dark matter right around where the band gap is, and then you get extra resonances where you get the extra shells of the dark matter. So this has been interesting. We put out a paper on this almost a year ago now, I guess. But there's a lot of papers out there which look for materials of weird complex conductivity that have resonances of a certain mass to look for bosonic direct pattern. So we'll talk a little bit about that at the end. So silicon doesn't really have one of those resonances for a good reason, so stay tuned. And then finally, the other uncertainty we have in all of these models is if you have a certain amount of energy, since we're measuring charge and not energy, there's some statistical fluctuations of how that energy redistributes into different numbers of charge carriers. So in the paper that we just wrote, we vary the width of this distribution. There's a parameter that controls it, but we don't really know it. As long as your background free, it doesn't matter. But if you have a strong background at 1 electron and you have a wide distribution, it doesn't affect you as much as if your signal is all in a single electron bit. So this is important. This is something that the CDMS collaboration is trying to measure in collaboration with all of the other light dark matter efforts. There's a few of them which I'll summarize shortly. But it's one of our biggest unknowns. So there's two things going on right now. Search for these electron recoiling dark matter models. So there's high resolution CCDs. And so these three efforts, Dami Sensei and Dane, are all driven by the same technique. It's this repetitive non-destructive readout. And the idea is you take a normal CCD, which if I read 1 pixel once, gives me a resolution of something like 4 or 5 electrons. And they've developed a technology where either by moving pixels in and out of the region or by allowing for multiple reads of a pixel with a sort of top-facing sensor, you can just read 1,000 times and you get square root of 1,000 improvement in the noise. And so you're basically trading readout time for readout resolution. So this is a plot from their first paper where they use the CCD and they do about 2,000 reads on a single pixel and they get sub-electron resolution. So the advantage of this technique is that you expose the CCD for an hour, you read it out, it probably takes about 10 minutes, and then you have excellent granularity on your events. You can see really cool things like tracks, cosmic rays are very easy to veto, leaves attractive material, different decays will leave different signatures. So they've done a lot of really cool work from Dominic from the earlier generation when they didn't quite have single electron resolution to show that they can project lots of cool backgrounds in a way that's not normal for a dark matter experiment. The downside though, as you can see here, is it takes them a long time to read out. And so while they're reading out, they're getting these dark rates. They're getting single photon counts just from thermal excitation. So that's why I say I think to be fair, the trade-off here is excellent position resolution for very, very poor timing resolution. I can only tell whether an event occurred within the hour exposure or at very best within a few minutes of readout. The other technique, so this is the one I work on, is to use athermal photon sensors. So Super CDMS, we've demonstrated this a few times, including most recently we put a paper on the archive on Sunday with actually a few people here are on that, Nader and Rupak. We're on that paper, and the method here is to take initial charge carriers you generate, put them through a large electric field, and if you have a large enough field, you basically just have a phonon energy that's proportional to the number of electron hole pairs you generate. So this was the original data demonstrating this technique, where we have no signal, we just have this Gaussian. So I put 30 photons in, I get a Gaussian that lines up with 60 ED, it's about 2 ED photons. And then if I jack up the voltage, I can stretch this out, and now I'm seeing a single electron, 2, 3, and then if I triple the voltage, I just drag this first peak up to 3 times the energy. So this was really nice. The benefit of this technique is that you can vary that voltage and move the peaks around, and if you get a high enough voltage, you can actually measure additional energy between the peaks to see whether you're getting full electron coverage or, full electron collection, electron hole collection, or whether you have any no charge events. But the downside obviously is you have these non-quantized events, which if this is a charge detector, that's not physical. And a lot of work we did over the last year was to try to figure out what that is. So we came up with a few models. Impact ionization is something that's very common in these devices. So things like avalanche photodiodes and silicon photomultipliers work. They multiply the charge using this process where a single electron can knock an additional electron off a new EV impurity state. You can have the reverse process where you just trap a charge Or, as we initially thought, you can have some infrared photon, which instead of having the electron free something, the IR photon can free these impurity states. You get a charge carrier that drifts not all the way across, but partially across the crystal, and you get an energy intermediate between the quantized peaks of the detector. So the theory that we came up with after the first run is, okay, this is probably IR. We've done a lot of work since to try to refine this. Initially, though, we did have really good evidence that this was the case. So our first paper, we had significant film regions. Our second paper, we did the dark matter analysis. We did a lot more IR filtering, and we got rid of these film regions. So this was, until recently, this was the record. We had a 10 eV resolution sensor. If you operate at 150 volts, it's about 700ths of the charge in resolution. But the dark matter search we did was weird. So this is the data that we got in our first dark matter run. There's a prominent single electron peak. There's a 2 electron peak. We can explain this region with impact ionization, but this stuff was sort of unexplained at the time. So we did something conservative. We said, assume that's the dark matter. You set an optimal observable limit, and for a lot of the mass range, we're limited by this stuff that we didn't understand. But we're pretty sure these are Compton scatters, but we weren't really sure what this was. So a lot of the R&D that's gone on since this has been to explain that, so I'll get to that in a little bit, maybe a couple slides. But the result looked like this at the time. So CDMS, we set limits on dark matter below what Xenon did back in, what Rubin did with Xenon's data back in 2011, and comparable to what was done by Dominic at the time. And resonances was the first place that all three of these limits, our limit, as well as the Sensei surface limit, and the Xenon and dark side limits were on the same blocks. I've been using it. It's a great blog if you haven't read it. But all three of these searches, at the end of the day, they're all limited to these dark counts. So we all have the same problem, which is that when we run our detectors with a good amount of shielding, we still get a high rate of single electrons. For Sensei, since they have not wonderful timing resolution, there's a high probability that one electron piles up on another one and produces 2 or 3. So that was the initial limiting factor here. And that was 0.02 gram days of exposure. We had half a gram day. We have much better timing resolutions, about 20 microseconds. And so our single to double peak is much lower. And then Xenon, this is order of 300 events total, but the high ionization energy limited them to a much lower mass. But at higher mass, they do much better than because they have a larger exposure. So let's skip this. The interesting thing that happened recently, so this is a paper that went up on Sunday. We ran a new device, and instead of running the first device where we applied the voltage directly on the backside of the crystal, we ran this contact-free mode that was largely pioneered by Notter, where instead of, we would use a ground plane opposite the face, the uninstrumented face of the detector to apply the voltage, so there's actually no interface for charge to leak across. And what we found was that all of these non-quantized weird events actually have a different distribution in this radial partition space. So if I compare the energy collected on the high radius part of the detector, the low radius part of the detector, my calibration source, either the cobalt or the SR55 or the laser, fills out a very different space than my leakage events. And I can actually use my 50% partition cut to remove 95% of those quantized events. So this is the first evidence that we can show, aside from me telling you I have a pretty good feeling that we can get rid of it, that we can actually start to reject some of these events. We take some exposure hit, but that's normal for a dark matter search. And the other thing that we showed in this paper was, so this is showing I can reject high radius events. The other thing we showed was that we can reject surface events. So if I have a significant coverage of sensors on either side of my crystal, and I use an iron 55 source, we can see this big blob. These are real events. If I jack up the voltage, I can move them to go to higher energy, so we know that they're in the bulk. These events don't move. We know that these are surface events, and they are in a different region of this amplitude versus integral space. So what that means is, when I look at an event in my time series data, It has a different pulse shape if it hits QT or if it hits on the surface than it does if it actually hits in the bulk, and I can use my voltage gain method. And so we're showing that between a pulse shape cut and a radial partition cut, we can fiducialize these detectors, where before we didn't claim we could do that. So this is significant. This means even if I have backgrounds, especially these non-quantized backgrounds, I can reject those. And because the mean free path of any X-ray below about 20 kV in silicon is on the order of millimeters or less, I should be able to reject almost all the backgrounds in my signal space. So we think that this is really good evidence that the next run of these detectors will be able to have significantly improved dark matter reach. So this is what I have been showing, how to overcome charge leakage. I think some of these conclusions are changed now. And some of them are the same. So we've shown we can reject some of this non-quantized leakage. We still expect that infrared will play a large role. So we've only run for fractions of a grand day. We need to run for a few hundred grand days. But there's a few things we can do, right? So more R&D, which is a lot of what's going on here for CDMS R&D, is different interfaces, different designs to mitigate this risk of charge leakage. We can make detectors which are inherently less susceptible, so they can have more tightly bound impurity states and are just less sensitive to IR, so that would be higher gap materials. And yeah, and now obviously these exotic things that I got to earlier. So one example that I want to show, so this is a paper we put out in January, basically talking about how you can use diamond as a dark matter agent. So diamond is actually semiconductor. It's exactly the same crystal structure as silicon and germanium. The differences are sort of threefold. It has a much lighter nucleus, it's carbon. It has a higher band gap. So for these electron recoil searches, it's sort of a compromise between something like silicon, germanium, and xenon. But it also has a much higher resistance to electric fields. So the polarization strength is stronger. It's harder to rip the electrons off the nuclei and induce some sort of linkage current. And what you get for those trade-offs is you get a much longer-lived, faster-moving, higher-energy phonon. So because the phonons and neutrons are tighter held, you also have deeper impurity states. So something like nitrogen, which in silicon has a binding energy of around 15 to 50 millieV, has a 1.7 and 4 eV binding energy in diamond. So a much different class of earth impurities. Lithium, again, about 10 times higher energy. And this has become interesting recently because the field of artificial diamonds has changed substantially in the last 18 months. So since 2016, the price of artificial diamond has dropped by 80%, from about $5,000 to about $1,000. And a bunch of labs are now making it. So Element 6 is owned by De Beers. Lincoln Labs is making this for qubit storage research, working with Element 6. It's become important to national security for various reasons, and so the DoD has started to fund this, and so the price has dropped further. Anyway, so you can get a 30 milligram diamond from a company for $2 grand. 30 milligrams is about 1 carat is 200 milligrams. So actually, if you want to buy your wife a diamond, you can go to this company Lightbox, and you can get a carat worth of diamond for $800. That's a guarantee they have. It's like $1,000 after setting and whatnot. But anyway, so this is really cool. And so the comparison I make in terms of economics, diamond is to sapphire, which people are already making detectors out of. Sapphire has been, you've been able to make sapphire very cheap for about 100 years, but you can still go out and buy your special someone a big sapphire and pay $40 million if you want to. So the difference between artificial and natural sapphires is psychological. And what the industry is trying to do is convince you that diamond is the same. So if you would please convince yourselves of that, then I can get some funding and buy some diamond and make some detectors. No, but in all seriousness, the big breakthrough has really been that De Beers has patented ways to determine whether it's artificial or natural diamond. So you can basically tell these apart from natural diamonds, and the companies can still make their money, and now people can make artificial diamond, and we can use it for things like high power electronics and for radiation detectors and quantum measurements. So I'll skip through some of the details of the experimental design. Or do I have to? Yeah. it's less interesting, I think. One thing I want to highlight, if I take a crystal and I want to make a calorimeter, this is what I would call the CDMS trade-off. This is really nice, simple calculation you can do. If you have a heat capacity attached to some thermal conductance, the minimum energy resolution you can get is sort of proportional to the volume and to the temperature cubed, the operating temperature cubed, which means that if you want something super sensitive, you can either make a really big thing at really low temperature or make a really small thing at a normal temperature. So the CDMS trade-off has been to make a medium-sized thing at a very low temperature to get very, very low thresholds. So what we'd be talking about is making cryogenic diamonds. The things that we have to show in order to say we can actually do this is that this efficiency, the actual ability to collect the energy from the diamond into a sensor, is not zero. So a couple things that came out of this initial paper. We looked at the difference in the mean-free path of phonons in diamond versus silicon and germanium. So diamond, if you can get really good isotopic purity, which you actually can, the diamond is grown from methane. It's primordial methane that's been sitting underground. All the carbon-14 for the most part is decayed off. You can't really make, I guess, people tell me you can't really make stable methane with carbon-13, so it's a high purity source. The upshot of that is the mean-free path is really long. It reaches its maximum at a much higher temperature than either silicon or germanium. So this is probably a more forgiving crystal. And this mean-free path increase really comes not from a scattering rate change, but from a velocity change. So these are faster phonons, and therefore, even though they have the same scattering rate as silicon or germanium, they can make it further.
So it's intrinsic, no? You are comparing the intrinsic germanium?
Intrinsic, yeah.
No intrinsic.
And in the paper, so I didn't do a good job of updating. This actually has an archive number now. This has been out since January. We plotted this against data. So there's, because diamonds have not been cheap, there's only a couple of groups that have done this. So there was a group of Russians who had a buddy in the diamond industry who gave them a handful of diamonds, and they found a really good one, and they measured the phonon mean-free path. And so we plotted it against the data. This matches up. This is largely size limited. So no one has made a meter scale diamond to measure the actual intrinsic.
So they look at reflections and it's many times reflecting.
Exactly, yeah. It's similar to the dual measurements. This is the Kozlov group in the 70s, I think. Right, so it has a great mean-free path. So the only difference really between a diamond substrate and silicon germanium, which we use in CDMS, is going to be the impedance between the diamond and the aluminum, which we use to collect phonons, and then the speed. So a grad student at Stanford did the calculations for this impedance mismatch of phonons between diamond and aluminum versus silicon and aluminum. It's a slight efficiency hit. You pick up almost all of the gains, if not more of the gains in resolution, just because you can collect the phonons faster. And then we can start to make projections for different detector designs. So in the paper, we propose a path from about 1 EV threshold detector, that would be about 30 milligrams, down to a 10 milli EV threshold detector, which again would be about 30 milligrams. So this is one R&D path. The second R&D path would be to go to slightly lower threshold with a gram to 10 gram detector. So these are interesting. I encourage you to read the paper. It's a fun paper to write, and we go through all of the different items you have to look into the diamond to convince yourself that this is a completely insane idea. So the goal here would be to get a diamond detector with a resolution good enough to resolve the optical phonons, which have an energy of 180 millieV. And then instead of this being just a calorimeter, it's actually a phonon spectrometer, which would be really cool. In diamond, the energy of those phonons is about 200 millieV. In silicon and germanium, it's more like 30 to 10 millieV. So, if you can make any of these detectors with a really good energy resolution, the diamond would be the spectrometer first. That'd be cool. We also have done now these structure factor calculations to calculate the rate. Again, the rate is highest in diamond in the single electron bin. We're also comparing here to, I think germanium is dashed and silicon is dotted. Again, in the paper, the legends are a little bit better. So basically, if you can make a single electron resolving detector, you can do pretty well. The argument we've been making for this detector is that since the band gap is higher and the impurity states are deeper, it should have a much better dark rate. And actually, everyone who has run the diamond detector has seen that even at room temperature, there's very little, if any at all, leakage current. And so you can play this game where I can draw, so now the germanium is blue, silicon is red, diamond is green. I can say for a 1 electron threshold, these are the 3 curves that matter. But if I assume that silicon and germanium are always going to be limited by leakage current a single electron bin, then diamond actually becomes comparable to them around this low mass of like 1-2 MeV, MeV, not MeV. By the time you get to about 10 MeV, it surpasses them. So if you can make a similar mass and a similar exposure, you can compete on par pretty much with silicon and germanium, both in the freeze in and freeze out spaces. If you have to go with a 2 electron threshold, though, it's much worse. And then these curves are for a gram day exposure. These curves are for the kilogram curve. So this is the give me $100 million limit, and this is the give me $10,000 limit. So this is sort of the range you can do. You couldn't really do much better unless the cost goes down by an extra 2 orders of magnitude for the The nuclear recoil range is more interesting though, because here you're just using it as a calorimeter. I've argued for why you can do really low thresholds, and then you get the extra bonus from the fact that it's a light nucleus. So if I compare helium, carbon, silicon, and xenon for the same energy threshold, assuming a dynamic range of 3 orders of magnitude, for a 1 eV threshold, in diamond I get down to about 50 MeV, versus helium is about 20 MeV, so it's tracking pretty close to helium, and then it does a lot better at higher mass. And then for the really low threshold, they're all going to do really well, but again with diamond you get a little bit lower mass due to that dynamic bonus you get. So that's what I have to say about diamond.
What are the colors again?
So
diamond, silicon, germanium?
So helium, diamond, silicon, and this is xenon.
Okay.
So germanium would be intermediate there. I'm also not claiming that you can ever make a xenon calorimeter with a 10 millieV threshold, but to be fair, it just uses the same assumptions, and it also assumes background free running, which again is an assumption. So I should say, after I wrote this talk, I gave it out in Chicago. Paolo Pertera pointed out that so for silicon 32 is the biggest problem, and this is it's caused by spallation, I think, or anyways, it's caused by cosmics in the source material, and so once you get a crystal, it's locked in. So for carbon, obviously carbon dating is a very well-known thing. So if you have the natural abundance of carbon in the diamond crystal, the event rate would be about 10 hertz per gram, which would obviously be really bad. But talking to the diamond suppliers, because they use this methane, which is sourced from underground, the time it takes to produce enough carbon-14 to get into equilibrium with the environment is on the order of thousands, if not millions of years. So as long as you use an underground source, you can make radio pure diamond, and then they do mass spec anyways on their gas after ionizing it. And so they already make highly enriched diamond, almost entirely carbon-12. So that's going to be a problem at some point, but it's going to be comparable to the silicon 32 problem rather than much worse than it.
What lead have been used for the here?
We've used the same as for silicon. There's a couple papers that explicitly treat the cascade, and they basically say below KeV it should do whatever silicon's doing. It's the same crystal structure. The only difference would be the optical phonon at that point.
And for helium, we just keep the light engine. It's a simulation for helium.
Yeah. Well, so it's not explicitly treating how you. It's assuming you can do this with efficiency written in Scott and Dan's papers. So it's assuming that they're right about what they can do with helium. Yeah. So in this roughly corresponds. This is it's approximately their second phase experiment would be a 1 eV threshold, I think. And then this is it's similar to what their final phase experiment would do. And again, yeah, so I should have to. So in the paper, we also have the carbon neutrino floor. It looks very similar to the helium.
So on the right side, you don't have ionization, it's a thermal parameter.
Yeah, this is just the protons.
So,
This is the superfluid helium.
so the Lehart doesn't matter.
No, this is just, so it's you get nuclear recoil, you break the proton state, the proton gets absorbed onto some CDMS detector, realistically. Okay, so this is something, this sort of covered what are these going on now and what's starting. The other things here are sort of more future ideas, but they're very cool. This is one of my favorite new ideas to come out recently. So Catherine Zurich and colleagues pointed out to describe the background a little bit before I actually show the calculation they did. In a solid, you have two phonon types, right? You have acoustic, which is just sound vibrations. You have optical, and the optical phonons they're a coherent oscillation between nuclei, right? And if you cool this thing really, really cold, then you limit the momentum space you can access here. And so what you actually see for this dispersion relation is you see a little band of optical phonons which look almost quantized, and then a continuum of acoustic phonons, and they're very well separated, right? And so if you can excite these optical phonons, this is sort of like a quantum in the same way the charge quantum exists, except it has an energy scale of milli-eV in the same crystals that we've been talking about, EV scale electronic stations. So if you find things like gallium arsenide or aluminum oxide, which is sapphire, you actually get in the photo absorption measurements resonances near the optical phonons. And the reason for this is because, so if you take the rate from this paper that they have, basically the entire rate depends on the difference between the high and low frequency dielectric constants, which is to say that if you can polarize the material very easily, you can get a resonance right around the optical phonon energy. So for polar materials, you can get this huge rate enhancement right around the optical phonon energy. If you warm it up, it gets a little bit broader. But basically, you can use these as very sensitive probes, bosonic dark matter for dark matter absorption. And so this left plot shows that. So, for sapphire, gallium arsenide, polycrystalline diamond also has a weaker phonon feature. You need to pair produce the phonons and some other sort of interface states. What's also interesting though is if you have a dark photon mediated dark matter, then this gives you an efficient sub-GeV scattering mechanism for the dark matter in one of these polar materials, and you can actually access the sub-MeV space. So this is pretty cool. So there's a group at LBL looking at gallium arsenide. There's a few people looking at sapphire, I think including you guys are starting to do some sapphire stuff. In the diamond paper, we also mentioned silicon carbide might be an interesting thing to look at. Has properties between silicon and diamond, both in terms of the band gap and the phonon properties. So these are pretty cool things, and all these are based on a kilogram year exposure, but they show you, even with if you scale this up to a gram, you're covering interesting parameter space. For the
also gallium nitride, that's also
nitride, yeah. So that's why I think this is useful, because you can look up these two, right? You need high frequency, low frequency, and optical phonon energy. You can pretty much set everything else to some reasonable number, and you can get an order of magnitude estimate. But the other thing is, so all these theory papers, they will calculate this spectrum, but at the end of the day, they always use the data because the data is never, So if you can find an absorption spectrum, you can pretty much predict this, and you just see where the peak is. So I think this is a link to the second paper where they actually do the DFT calculations for sapphire was complicated. One of these, I can't remember which one. One of these was very easy and they did an analytic approximation. And the other one is very complicated because they have a non-trivial band structure. I want to say sapphire was much harder. But so this is done, and there's a framework for this, and we are talking to. We'll have a paper out in a couple months for silicon carbide as well. So the last thing, obviously, is the superconducting detector R&D. So this is more pie in the sky. So if you read like Cosmic Visions, for example, they have this whole table of here's this effort and this is the time scale. This is always 10 plus years, mostly because it's super cool, but it's also the most technically challenging. I think it's also going to be one of the most rewarding things when we get to work. The thing I like to point out is that this isn't new. So this figure is from Rick Gateskill's thesis, 1993, right? So the Oxford group was working on this. Literally, WIMP scattered from niobium. So what happened between here and now? So Rick wrote his thesis. Kent Merwin and Bloss invented the TES. They started doing dark matter and silicon. This got put on the shelf, right? They said, well, this is overkill. You know, getting an operating niobium crystal is just a huge pain. So let's go with the silicon thing. So I think we're now at a time where we're starting to say, okay, we've taken silicon and germanium almost to their limits. We need to go back to superconductors. And a lot of the work done in this thesis was very promising. You can get excellent quasi-particle free paths. A lot of the fab issues have been worked out. But I think there's real challenges in cooling this thing since a superconductor becomes a thermal insulator as it goes through the transition. Electrical readout is going to be more complicated. So there was a paper, Matt Pyle and Yoni Koshberg and Catherine Zurich explored some of the early issues that you immediately would encounter and talked about how you fabricate a quasi-particle trap on a 5 millimeter aluminum cube. So people talk about aluminum, niobium, tantalum, tungsten. Essentially, what you're leveraging here is the fact that I can go back to BCS theory and I can look at quasi-particle and phonon lifetimes. And so as long as I cool the crystal well below its TC, I can get basically a divergent lifetime for all the quasi-particles right at the band gap edge. And I can get basically no phonon scattering right at that edge. I can just have the quasi-particles bounce around forever, with the exception that they'll recombine. And you can quantify this. You can quantify all of the different carrier lifetimes in these materials. There's different trade-offs. So between niobium, aluminum, and butane, lead, they have different TCs. They have different binding energies, and then they have different phonon spectra, right? So the TC is determined by the quasi-particle phonon dynamics to a certain extent. And you can either use these as quasi-particle readout devices or phonon readout devices. What makes it complicated is that the quasi-particles and phonons are not decoupled. So actually, there's this effective lifetime. This is the relevant thing. The effective lifetime of the quasi-particle is milliseconds. But what's actually happening is on the picosecond scale, you break the Cooper pair, you make quasi-particles, they recombine and emit a phonon, and that immediately breaks the Cooper pairs again. So you have this mixed state. And so one of the challenges, even understanding how these detectors are going to work, and what the signals are going to look like, in contrast to silicon and germanium, is you don't have these free particles that are basically free streaming. You have this highly correlated mess of stuff, and you really need to figure out what the rate balance is between these two processes and what the inefficiencies are and how you actually lose your time. So I think from the theory standpoint, in terms of the solid state theory, this is interesting. So a few of us are doing some calculations on directionality of the actual recoil in superconductors, basically seeing does a superconductor have a Cherenkov cone of phonons, yes or no? That should be pretty cool. But it's an interesting solid state system.
There's no way to do the kinetic inductance measurement of this. No? Kinetic inductance measurement with this thing is not going to work because you have such a large mass that.
Yeah. Yeah.
There were no attempts on that. No.
No. I mean, you could do kits. So there are some papers on using arrays of M kits and nanowires and stuff. Nanowires, I think there was some paper the last couple of weeks. But the mass is challenging. So for a milligram scale cube down to certain exposures, these are some of the predictions. So I'll put you in the paper for more details. Basically, there are plenty of models. This is the Xenon 10 limit that exists. There are plenty of models that these cut through interestingly. And if you compare it to germanium, which is the lowest band gap semiconductor, you get significantly lower mass reach. So you get down to this KE4, which, as I said earlier, that's about as low as you care about fermion and dark matter from optical constraints. So this is pretty much the thing that people think will really get us down to the lowest masses we can do direct detection for that are fermion. The bosonic picture is different, and there's obviously different experiments, and that's not right here. So the last couple months, I've been trying to collect a list of all the R&D efforts. This is semi-complete, so this is the stuff that I consider more mature. Right, so silicon, there's a lot of efforts. Ptolemy's been working on graphene, both FETs and nanotubes. I don't really know what the status of that is. Trying to reach out to them. For photon detectors, again, we have a large group of detectors. This LBL UMass group put out a paper back in, I guess that's October, most recently sort of summarizing their status. Gallium arsenide is being worked on at LBL as a scintillator, as well as this optical photon detector. And then Sapphire, I think there's actually a more recent paper than this now. Nucleus, which is a coherent neutrino scattering experiment, as well as a dark matter experiment, has been working on Sapphire, and then, of course, this HEPEC group here is starting to do this as well. All these other things are at the conceptual stage, but there are definitely people starting to jump on. So superconductors, I know there's a group of us starting to think about this. LBL group is starting to work on germanium. These things are cool. No one's actually working on them yet, but that'd be interesting.
So the Caltech group is on superconductors thermal measurement, phonon measurement, or on kit?
Yeah, I think Sunil's interested in trying to do
It's Sunil.
Yeah, so we've been talking about trying to put together a proof of concept for a thermal measurement. And whether this is really thermal, where you just hook up the Tolly and Matt's idea of this thermal gold contact that goes through a TPS, or whether that's actually purely red. And they already work on the M kits. They have fab expertise from now, being rolling them. It's sort of a natural tie-in. So we've just been talking about this. This is totally conceptual. The diamond stuff is actually, we're starting to put crayons in, so that's actually becoming a reality. Lots of exciting ideas. So we're having a workshop at Fermilab in June, focused on Sub-GeV dark matter, which the main result of which I hope to have a list of all of the ongoing efforts and the actual status and prospects, and maybe even a plot. That'd be excellent. But until then, these are the plots we have, still from Cosmic Visions. Depending on what the dark matter is, you can do better or worse, above an MeV. I think we still agree that basically your rock materials or superconductors are the only ways to go below an MeV. But this space is interesting. There's lots of theoretically motivated models here, and it should be fun. So it's, these are experiments you can do in a lab, in the basement of the university, for not too much money in a couple days right now. That's what we're doing. It'll get back to the sort of kilogram year stage eventually, but right now this is lab physics. It's very cool. So yeah, takeaways, a lot to do. One big thing that we're really starting to confront is that the low energy electron recoil backgrounds are largely unknown. So for example, things like plasmon resonances and semiconductors at cryogenic temperatures, there's no literature on that. So we have no idea what's going on. We're trying to characterize it. But I think, and coherent photon scattering, all that stuff. If anyone out there is a phenomenologist who likes to model solid state weirdness, this would be a very cool thing to start writing papers about. And then there's lots of new investment. So DOE is very interested. There's a lot of tie-in with QIS, so it's pretty active. Thanks.
Thank you very much. Are there any questions?
I think one thing people need to understand, we're not in the detector field, is not just the detector technology, but the backgrounds. Many of these new technologies, they will be, there's nothing, the reason we do germanium is not just, it's cool and easy, but the radio purity and the electrical impurity is sort of the best thing. But to get to that stage where any of those other things like diamond and helium to be naturally radio pure, it would take a long time. Could take a long time.
Could take one.
Right.
Yeah.
So once we demonstrate the detector technology to get to the where you can do science with the
Yeah.
How do you know you completely mitigated the leakage current?
Oh, I mean, you mean the plots I showed from this recent paper? Yeah, so I mean, there's still some leakage beyond this cut. This was just a demonstration of, let's map out the partition and see, if we take this cobalt source, which is uniformly distributed energy in this range and sort of all over the detector, use that to measure the efficiency of the cut, and then apply the cut and see what happens to the leakage. I mean, if we quantify the ratio of this to that, it's about 20 to 1. So it's not totally gone. We can also sort of control this rate by doing all sorts of neutralization things, but we went from, I think the science run we claimed there's no way to, we can't claim there's any way to get rid of this. Here at least we're saying there's a way to reduce it. And the stuff that passes this cut looks more quantized. This is also, it's also possible that the thing we chose as, the cigarette paper that we used to hold the detector sort of wedged in this little apparatus, maybe there's leakage through that.
Or maybe it has some charge.
Or it has some charge, yeah. So, one thing we can try is move that to the center, see if the leakage moves.
So one thing I've noticed here that's interesting is the laser events, those are the ones in red, right?
Yeah.
They go all the way to the bottom and a little further up in the amplitude, right? But the background's all sort of focused there at the bottom.
Yeah, well, a lot of this is noise. So this uses a sliding optimal filter, which pushes some of the true zeros to finally. But this is the majority of the background. There's this band that goes from a single electron down. Historically, we've also seen that when you get really bad leakage, you get all sorts of weird stuff up here, but it's always behind the partition. It's always removable with a cut. So this is sort of like, CDMS detectors, we've done this with like CDMS light. You usually want to cut out the high radius region of the detector for a whole host of reasons. So it's, we're showing we can do that.
Just a comment about whatever we do, the calibration should come after. We need to have a good plan for how to calibrate them to the electron volt or electron volt, recoil, and so on. So
Yeah. So we were hoping with this plasma. So we used the cobalt because it has a high enough, has a long beam free path. And we were hoping we would see this. There's a plasmon resonance in silicon at 14 eV.
Yeah.
You're hoping there'd be a line. It's a feature.
Yeah.
The rate's really low. No, we have a calculation now. So maybe there's a feature, but it hasn't been measured. And then, there was Alan's paper about coherent photon scatter. That has a feature at sub-EV energies. But how you calibrate, 1 milli EV is not even close to being, I don't know, being has even
Any other question? Okay, no, we'll be around until tomorrow afternoon. Let's back one more time.